Exponential integrability in probability spaces is revisited, with novel results introduced and existing ones quantified. The work builds upon recent findings by Cianchi-Musil and Pick, providing a quantitative form of Moser-Trudinger-type inequalities. Furthermore, it recovers Ivanisvili-Russell's inequality for the Gaussian measure through a dual argument, a novel approach in this context. This methodology is also applied to the discrete setting of the Poisson measure on integers. The foundation of this work lies in the logarithmic Sobolev inequality, a fundamental concept in mathematics with connections to convex geometry, information theory, and statistical mechanics. The authors generalize this inequality by replacing the Euclidean space R(n) with a metric space X and introducing a derivation operator in place of nabla f. This inequality holds in both continuous and discrete settings, such as on a graph with an appropriate Dirichlet form. For a Borel probability measure micro on R(n) satisfying the logarithmic Sobolev inequality, the authors demonstrate that the exponential inequality holds for all smooth functions f with integral fd micro equals 0 and an arbitrary value alpha greater than c. The classical example of the standard Gaussian measure micro equals gamma underscore n is provided, where c equals 1/2 is optimal. The Barki criterion is also discussed, stating that the logarithmic Sobolev inequality holds with constant c equals 1, 2 rho, for any micro with density v, x, satisfying Hess. V is greater than or equal to rho greater than 0. This research contributes to the advancement of exponential integrability in probability spaces, with potential applications in various fields. The paper delves into various exponential inequalities, particularly those related to the Moser-Trudinger inequality, which is a dimension-free result within the context of Gaussian measures. These inequalities are crucial for understanding the interplay between the norm of a function and its gradient in different settings. The authors focus on the family of Sobolev-type relations, where the integral of a function with respect to a probability measure is bounded by a functional of the integral of the gradient of the function. In the gamma-2 formalism, the authors employ the semi-group technique to sharpen existing inequalities, leading to better exponents in the bounds. They also derive local inequalities for the semi-group in place of the measure. For sub-Gaussian measures, they extend the approach of a previous work by introducing a modified log-Sobolev inequality. This leads to new exponential inequalities for measures with sub-Gaussian tails, such as those with densities proportional to express minus x, p element of 1, 2, on each fiber. The paper provides a comprehensive overview of the current state of knowledge in this area and presents novel findings that contribute to the understanding of the interplay between the norm of a function and its gradient in different contexts. In the realm of probability spaces, exponential inequalities play a crucial role. This section delves into the intricacies of perturbation, stability, optimality, and reduction of these inequalities. The cornerstone of this discussion is Theorem 2.1, which establishes that a bounded perturbation of the probability measure does not affect the validity of the exponential inequality, provided certain conditions are met. This theorem leverages Lemma 2.2, which furnishes an expression for the integral of a convex function over a probability measure, and is proven for completeness. The section also explores the stability of the inequality under bounded perturbation, demonstrating that the inequality remains valid when the probability measure is perturbed within specific bounds. Furthermore, the authors show that, under mild assumptions, the constraint or integral of the function can be transformed into a median constraint. The Erhard's rearrangement technique is employed to prove that the exponential inequality can be reduced to a unidimensional problem for non-decreasing functions satisfying specific conditions. This reduction is achieved by considering a class of functions known as Hardy-type constraints. The optimality of the obtained results is also discussed, suggesting that they cannot be significantly improved upon. The section provides a comprehensive analysis of exponential inequalities in probability spaces, offering novel insights and techniques for dealing with these inequalities in various contexts. The results presented here have far-reaching implications for the field, providing a deeper understanding of the intricacies of exponential inequalities in probability spaces. The proof of Theorem 2.1 begins by applying Lemma 2.2 twice to the function phi, x, equals x. This process leads to an inequality involving the integral of f with respect to the measure nu and the integral of f with respect to the measure micro. The convexity of phi ensures that the integrand is non-negative, resulting in an upper bound for the integral of f with respect to nu. The concept of strong log concavity of a probability measure micro on Rn is introduced, defined as having a log concave density with respect to the standard Gaussian measure. Theorem 2.3, attributed to Caffarelli, states the existence of a 1 Lipschitz map T Rn right pointing arrow Rn that pushes forward the standard Gaussian measure gamma n to micro. Proposition 2.4 provides an elementary yet useful result, stating that if f and g are non-decreasing and continuous functions, and micro is a strongly log-concave probability measure on Rn, then a certain inequality involving the integral of a function f with respect to gamma n implies a similar inequality involving the integral of a function g with respect to micro. The proof of this proposition involves extending the hypothesis from smooth functions to locally Lipschitz functions, and using the Lipschitz map T from Theorem 2.3 to establish the desired inequality. Applying the exponential inequality to f with respect to gamma n, we obtain an upper bound for the integral of e⁻g d micro in terms of the integral of g, nabla f, d gamma n, which is further bounded by the integral of g, nabla g, t, d gamma n. This leads to an inequality involving the maximal function f and the Orlitz's norm of nabla g, with respect to the measure micro. The authors then explore the connection between the condition of zero mean and zero median in the context of exponential inequalities. They consider a specific example where f, t, equals e⁻t and g, t, equals 1, 1 plus t e⁻t 2 halves, and demonstrate that the inequality holds under the condition of zero median, mf equals 0, where mf is the maximal median of f under the measure micro. The authors recall the Moser-Trudinger inequality, which states that a probability measure micro on Rn satisfies the inequality if there exists a constant c such that for all smooth f, the integral of fmf d micro is bounded by c times the integral of nabla f d micro. This inequality is equivalent to an isoparametric type inequality relating the micro-perimeter of a set A to its microsize. Assuming that the logarithmic integral of e⁻f d micro is bounded by a times the integral of g, nabla f, d micro for all f with zero mean, the authors apply this inequality to a smooth function g with zero median, mg equals 0. By using the Moser-Trudinger inequality, they establish a bound for the integral of g d micro in terms of the integral of g, nabla g, d micro, which leads to an exponential inequality involving the integral of e⁻g d micro. The authors conclude that the two conditions in the exponential inequality are equivalent, albeit with some loss in the constant, demonstrating the connection between the zero mean and zero median conditions in the context of exponential inequalities. In the context of a dual convexity argument, the optimality of the function g, t, equals et 2 halves, radical big 1 plus t 2 halves is discussed. An inequality is presented, stating that for any function f with integral text f d gamma n equals 0, log, parent left big, integral display ef d gamma n, parent right big is less than or equal to 8, integral display, nabla f, 2 halves, radical big 1 plus, nabla f, 2 halves, d gamma n. The unidimensional case is then examined, demonstrating that the inequality log, parent left big, integral display ef d gamma, parent right big is less than or equal to, integral display f d gamma plus f, parent left big, integral display ef, 2 halves h, f, d gamma, parent right big cannot hold if the function h behaves like t, lot, 1 plus epsilon for large t. This excludes certain functions and suggests the biggest admissible function h lies between t and t log tat infinity. The section concludes by observing that for h, x, equals 1, an inequality of the form, integral display ef d gamma is less than or equal to, parent left big, integral display ef, 2 halves d gamma, parent right big 2 could hold for all f with mean 0 with respect to the Gaussian measure. The Gaussian rearrangement of a Borel set A in Rn preserves equimeasurability between f and f** operator, leading to a polyazygo type inequality for non-decreasing convex functions g. This inequality enables dimensionality reduction, demonstrating that the unidimensional version of the exponential inequality is sufficient for proving the n-dimensional case. We introduce the notation f2, x, as a sup of the sum of f, x1, and f, x2, under certain conditions, which simplifies analysis when f is non-decreasing and convex. Furthermore, Hardy's inequality is presented, stating that a measure micro on the line satisfies this inequality if it meets a specific condition involving integrals of ff, 0, and f. By employing the Gaussian rearrangement technique and the properties of f2, x, we prove that if the exponential inequality holds in dimension n equals 1 for all non-decreasing smooth functions, it also holds in any dimension n. This result has significant implications for the study of exponential inequalities in probability spaces and their connection to Hardy-type inequalities on the half-line. The lemma establishes an exponential Hardy-type inequality, assuming f and g are non-decreasing functions from 0, infinity, to 0, infinity, and micro is a symmetric probability measure on the line. For all smooth functions g, r right pointing arrow r with integral infinity sin infinity g, g, d micro less than infinity, the inequality states integral infinity sin infinity e g d micro express integral infinity sin infinity g d micro is less than or equal to e.g. 0 f squared integral infinity sin infinity g, g, d micro. The proof begins by applying lemma 2.2 with phi x equals x and t equals g, 0, equals 0, yielding an upper bound for the left-hand side. This is then split into two integrals using the definition of f plus and f functions, constructed such that g is less than or equal to f plus on the positive axis and g, x, is less than or equal to f, x, for all x is greater than or equal to 0. The proof continues by using the symmetry of micro and the fact that x rightwards arrow from bar xx is increasing on 0, infinity. This allows the authors to bound the integrals involving f plus and f using the assumption stated in the lemma. Finally, the desired inequality is obtained by combining these bounds and using the fact that f squared is non-decreasing. The remark highlights the symmetry of micro, explaining the factor 1/2 in the inequality, and notes that the inequality is invariant under adding a constant to g. For g with 0 mean, the inequality is strengthened to integral infinity sin infinity e g d micro is less than or equal to 1 plus express a integral infinity sin infinity g, d micro, f squared integral infinity sin infinity g, g, d micro, where a is a constant. In probability spaces, the authors investigate exponential inequalities, specifically focusing on the Gaussian measure gamma 1. They derive a Hardy-type inequality featuring a constant a equals square root pi, 2, proven to be optimal using Muckenhaupt's result. This inequality is subsequently applied to establish an upper bound for the integral of an exponential function with respect to the Gaussian measure gamma n in dimension n. The lemma incorporates a condition for the exponential function to be non-decreasing and smooth, contingent upon the assumption that the integral of the function g with respect to gamma n is 0. Notably, the authors highlight the limitation of the inequality, 13, when the maximum value of x in the definition of d is infinite, rendering the right-hand side infinite and thus ineffective. The authors of the research paper introduce the gamma formalism, a mathematical framework based on an abstract Markov generator L, which is self-adjoint in L2, micro, with a domain D, L. This formalism is associated with a semigroup, Pt, T is greater than or equal to 0 and uses a set A of good family of functions that are dense in all Lp, micro, 1 less than P less than infinity. The set A is assumed to be stable under the action of Pt, T greater than 0, and L, and by composition with any C infinity smooth functions. It also contains all constant functions and lim T right pointing arrow infinity sign PTF equals integral FD micro for all F in A. The Carré-Duchamp operator gamma, F, G, and its iterated form gamma 2, F, G, are defined, leading to the introduction of the gamma 2 condition. This condition states that L has curvature row element of R if gamma 2, F, is greater than or equal to Rg, F, for all F in A. The authors provide examples of A for the Ornstein-Uhlenbeck process and for compact connected complete Riemannian manifolds, noting that the Ornstein-Uhlenbeck operator in Rn has curvature ρ equals 1, and the operator L equals increment plus nabla V, on a manifold with Ricci curvature bounded below by R, has curvature bounded below by ρ if R plus nabla V is greater than or equal to ρg, where G is the Riemannian metric. An exponential inequality is established using the integral of e.g. d gamma 1, obtained by applying proposition 2.5 to the expression f2 x equals f x plus f 0 equals aebx2c, where f x equals aebxc. This inequality is crucial for further analysis in the paper. The development of exponential inequalities in probability spaces is a pivotal aspect of this research paper, focusing on the semi-group approach to inequality 2, under the gamma 2 condition. A local version of this inequality is introduced, involving the semi-group PT and representing a stronger statement compared to previous works. However, the authors acknowledge that their approach is less robust than the one presented in 10, as it deals with less general situations. The paper commences by highlighting the main features of the general framework, including the commutation of the semi-group and the Carré-Duchamp operator, and the diffusion property of the operator L. An integration by parts formula for f, g element of A is then presented, and it is explained that the diffusion property implies a crucial consequence, namely, the equality in 17. The authors then introduce theorem 3.1, which states that if the Markov diffusion operator L satisfies the curvature condition gamma 2, f is greater than or equal to Rg, f ρ greater than 0, for all f in A, then for all f and all t greater than 0, the following inequality holds. Log pt, ef, ptf is less than or equal to c alpha, t, log pt, eag, f, where c alpha, t, is a specific function of t, and alpha greater than e2 ρ t plus e2 ρ t2, 2 ρ, e2 ρ t1. This result represents a semi-group approach to inequality 2, under the gamma 2 condition, providing a local version of the inequality that involves the semi-group PT and is stronger than previous results. In conclusion, the paper notes that the approach presented here is less robust than the one in 10, as it deals with less general situations, but it also gives a stronger statement due to its involvement of the semigroup PT. The properties of the function f are examined in relation to the integral and the parameter alpha. A key inequality is established, involving alpha, ρ, and the integral of f with respect to micro. This inequality is then leveraged to derive a stronger version of a previously known result, showcasing the intricate connection between the curvature condition and the local log Sobolev inequality. Notably, the proof relies on the diffusion property and the entropic inequality, illustrating the interplay between these concepts in establishing the stronger inequality. The curvature condition is found to have significant implications for the local log Sobolev inequality, underscoring the importance of this relationship in understanding the properties of f. Through this analysis, the paper provides a deeper understanding of the integral's role in shaping the behavior of f, while also highlighting the critical role of alpha in modulating this relationship. The derived inequality offers a more nuanced appreciation of the interdependencies between alpha, ρ, and the integral, ultimately contributing to a richer understanding of the function f. The text discusses exponential inequalities in probability spaces, revisiting previous results. It starts by establishing a crucial inequality using the commutation property, ensuring a licit choice for theta. This setup allows the application of lemma 3.4, which yields an upper bound for a specific expression. The proof then employs Jensen's inequality to further refine this bound, ultimately leading to an expected result. The discussion also highlights a remarkable, cruder argument based on Jensen's inequality, which provides an improvement in the limit t right pointing arrow infinity. This section concludes by mentioning the use of lemmas in the proof of theorem 3.1, emphasizing the importance of these lemmas in establishing the main results. The research paper discusses two lemmas crucial for analyzing a specific property in the context of a diffusion process. The first lemma establishes a local hypercontractivity property for the measure Pt, equivalent to 3, theorem 3.1. This property is essential for understanding the diffusion process's behavior and its relationship with the invariant measure micro. The proof involves using the diffusion property and applying the local log-Sobolev inequality. The second lemma presents an integral identity used later in the paper to derive other results, involving a complex integration over a specific range. By changing variables and applying algebraic manipulations, the authors simplify the integral and obtain the desired result, connected to the curvature condition. These lemmas contribute to the paper's main argument by providing fundamental properties related to the diffusion process and its connection with the invariant measure, essential for understanding the system's behavior and deriving further results. The paper delves into the extension of exponential inequalities in probability spaces, with a particular emphasis on sub-Gaussian measures. A key assumption in the original approach to derive these inequalities is the log-Sobolev inequality, which holds for measures with densities proportional to e(x)(p) on the line, where p is greater than or equal to 2. However, this approach cannot be directly applied when p element of 1, 2, due to a lack of commutation property in the diffusion semigroup associated with such measures. To address this limitation, the authors introduce a modified log-Sobolev inequality, which they prove for measures micro p with p element of 1, 2. This inequality is equivalent to Clog-Sobolev inequalities studied in depth by other researchers. The authors also cite previous works by Gentil, Gillen, and Miklo, who established a modified log-Sobolev inequality for micro p when p element of 1, 2, with a specific choice of function h that compares to max x squared x caret q, where q equals p1, p greater than 2. The paper then presents a theorem that states if a probability measure micro on R(n) satisfies the modified log-Sobolev inequality with a non-decreasing convex function h. R right pointing arrow 0, infinity, vanishing at the origin, and x square root h x right pointing arrow h square root x is also convex, then for all locally Lipschitz functions f R(n) right pointing arrow r, certain exponential integrability bounds can be derived. These bounds are crucial for understanding the concentration phenomenon in probability theory and have implications for various applications in machine learning and statistics. The Lipschitz function f Rn right pointing arrow r, with its integral over a measure micro equaling 0, is discussed. An inequality involving the function's derivative, the measure, and a constant alpha is presented. This inequality is used to recover the classical log-Sobolev inequality. The discussion extends to more general log-concave measures with tails between exponential and Gaussian. The optimal constant in the inequality is unknown, except for the Gaussian measure. The proof utilizes the variational characterization of entropy and Herbst's argument, involving the modified log-Sobolev inequality and the introduction of a new function omega x. The convexity of h square root x implies the convexity of omega square root x, and subsequently beta, since omega 0 equals 0. This leads to the non-decreasing map t right pointing arrow beta t, resulting in the inequality beta lambda squared is less than or equal to beta 1. This inequality is then used to derive the bound log g 1 lim lambda right pointing arrow 0 lambda log g lambda is less than or equal to c alpha c beta 1, which ultimately yields the desired conclusion. The authors revisit the concept of exponential integrability of second order, previously explored in 17. They present a quantitative version of this statement for the special case beta equals 1, extending the results to a broader class of measures on R(n) that satisfy the log-Sobolev inequality, including measures that are not strongly log-concave. Theorem 3.9 states that if a probability measure micro satisfies the log-Sobolev inequality, then for any alpha greater than c and f with integral f d micro equals 0, the inequality log integral e f d micro is less than or equal to c alpha c integral e alpha lf d micro holds. Additionally, the bound log integral e f d micro is less than or equal to c e caret alpha plus log 2 plus 2c alpha c integral e alpha lf d micro is derived. The proof of theorem 3.9 relies on the diffusion property and integration by parts, recasting the log Sobolev inequality as ent micro EF is less than or equal to C integral EF, LF, d micro. The entropic inequality is then applied to obtain the desired bounds. Notably, for the Gaussian measure, C equals 1/2, and the constraint alpha greater than 1/2 agrees with the optimal threshold beta, 2 equals 1/2 of 17. This result highlights the significance of the log Sobolev inequality in characterizing exponential integrability of second order, and provides a broader framework for understanding this concept in various measure spaces. The authors derive an inequality for the entropy of a function f with respect to a measure micro, denoted as ent micro EF, using homogeneity and Herbst's argument. Specifically, they show that for any t greater than c, ent micro EF is less than or equal to c tc log integral e caret tlf d micro. Applying this to lambda f, they obtain an inequality involving the entropy of e caret lambda f, which is then rewritten in terms of h lambda equals integral e caret lambda f d micro. By dividing both sides by lambda caret 2h lambda and using Jensen's inequality, they arrive at an inequality for the derivative of log h lambda lambda, which is bounded by a term involving the integral of e caret t lambda lf d micro. To overcome the lack of integrability of the right-hand side at lambda equals 0, they expand the exponential using the reversibility of the measure, which implies that integral lf d micro equals 0. This leads to a bound on the integral of e caret t lf d micro, which is used to derive the first part of the theorem. The second part of the theorem is a consequence of the first, and is obtained by applying the first part to f plus and f, where f plus equals max f 0, and f equals max f 0. The final inequality involves the integral of f d micro and the integral of e caret alpha lf d micro. The authors use precise inequalities, such as log 1 plus x is less than or equal to x and log a plus b is less than or equal to log a plus log b plus log 2, to derive their results. The section of the research paper focuses on exponential inequalities in probability spaces, revisiting a particular form of the exponential Hardy-type inequality. It begins by establishing a Poincaré inequality using the log Sobolev inequality. This inequality is then used to derive a bound for the expectation of the square of a function, providing an estimate for the variance of the function in terms of its gradient. The main result is theorem 4.1, which presents an exponential Hardy-type inequality for functions defined on the real line. This theorem states that for any function f with f 0 equals 0, the logarithm of the expectation of the absolute value of f under the standard Gaussian measure is bounded by the integral of the square of the derivative of f divided by the square root of 1 plus the square of the derivative, all multiplied by a constant factor. The theorem has implications for the study of exponential integrability of functions and their gradients in probability spaces. Corollary 4.2 demonstrates how theorem 4.1 can be used to recover the exponential inequality 3 for functions with zero mean under the Gaussian measure in any dimension. This corollary provides an upper bound for the logarithm of the expectation of the function in terms of the expectation of the square of the gradient of the function, normalized by the square root of 1 plus the square of the gradient. The paper also employs a convexity argument in section 4.1 to provide an alternative proof of inequality 3. This approach involves using duality principles from functional analysis to establish the desired exponential inequality. The use of convexity arguments allows for a more general treatment of the problem, encompassing a broader range of situations than the initial proof. The proof of corollary 4.2 relies on the exponential Hardy-type inequality established in theorem 4.1. This inequality satisfies the assumptions of lemma 2.9, where f, x, and g, x, are defined as exponential functions. The maximum value of g, x, is approximately 0.9602, which is used to bound the expression for log integral EF d gamma n. By applying lemma 2.9, an upper bound for log integral EF d gamma n is established in terms of integral g, nabla f, d gamma n. The decreasing function psi x on infinity enables further bounds to be established, ultimately leading to an upper bound for log integral EF d gamma n in terms of integral Rn nabla f squared 1 plus nabla f squared d gamma n. The proof of theorem 4.1 begins with an application of Young's inequality to f x, resulting in an upper bound involving the functions g and g. The proof then focuses on bounding the second term in the resulting inequality, which requires a detailed analysis of the function g and its asymptotics. The function v x is introduced, and its properties are used to define w x and h x, which are increasing functions. The inverses of w and h are defined, and the proof concludes with the introduction of the constant τ equals h1. The precise bounds and inequalities established in these proofs have significant implications for the understanding of exponential Hardy-type inequalities and their applications. The proof for exponential inequalities in probability spaces continues with the function g** operator, y, which is related to w, x, and v, x. It is shown that g** operator, y, can be expressed as a function of x, where x equals w minus 1, t squared, 2, and the monotonicity of w ensures a correspondence between the notations 0 to and xo 4. A key step in the proof involves bounding an integral involving g** operator et squared 2 by 5.14. A technical lemma, lemma 4.3, is introduced to provide further insights into the functions v x, h x, and w x. These functions are defined as v x equals x squared 2 1/2 log 1 plus x squared 2 h x equals square root 2x 1 plus x squared cubed to the power of 5 squared, and w x equals v x plus log v x. The lemma states that h x is an increasing function, mapping 0 infinity to 0 square root 2, and defines τ as h1. This lemma serves as a foundation for subsequent analyses and proofs in the paper. The authors present a series of inequalities and properties related to the functions v, w, and h, which are crucial in the analysis of a particular machine learning model. They establish 4 key points: the existence of a value τ in the interval 2.13, 2.14, a value xo in 1.05, 1.06, ensuring the map w is increasing, the inequality x caret 1 v x square root 2 w x is less than or equal to 0 for all x is greater than or equal to xo, and another inequality for x is greater than or equal to 4. To prove the second inequality, the domain is divided into 2 regimes. For x in xo 21/4, it's shown that x caret 1 v x square root 2 w x is less than or equal to x caret 1 v x is less than or equal to 0. In the second regime, the monotonicity of h on 21/4 τ is used. For the fourth point, equation 22 is utilized, along with the fact that v x is less than or equal to x, to establish the desired inequality through numerical computations. The authors rely heavily on numerical computations and the monotonicity of h to prove these points. The extension of exponential inequalities in probability spaces is a crucial area of research, with a focus on developing new exponential Hardy-type inequalities. A novel theorem is presented, introducing a constant c beta that depends on the parameter beta, bounded between square root 51 and 2. This constant is pivotal in enabling the extension of previous approaches to more general exponential inequalities. The proof of the theorem follows a similar structure to theorem 4.1, leveraging Young's inequality and the concept of conjugate functions. The key idea is to identify an appropriate function g such that the integral of f x can be bounded by the integral of g f t plus another term involving the conjugate function g by selecting g x equals e caret v x, with v x equals kappa x caret beta, where kappa equals square root 2 beta beta plus 2 the authors derive an expression for g in terms of the inverse function w(1). This leads to the final form of the exponential Hardy-type inequality, providing a bound on the integral of f x squared beta plus 2 in terms of the integral of kappa f t caret beta. Notably, the constant c beta has a specific form that diverges at both beta equals square root 51 and beta equals 2, indicating that these values are critical for the validity of the theorem. The authors also highlight that the case beta equals 2 was independently considered in Theorem 4.1, and that they were unable to extend the semi-group approach developed in a previous study to prove this theorem. Furthermore, they suggest that with additional effort, it is possible to improve the right-hand side of the exponential Hardy-type inequality by adding an extra factor in the denominator, involving an increasing function h. The authors define a set M and a value x, which are used to establish an inequality involving the function g and its conjugate g. The inequality is derived by applying lemma 4.6, which guarantees that g et squared 2 et squared 2 is less than or equal to 0 for all t element of 0 x. The inequality is then rearranged to obtain an upper bound for the integral of e f x squared beta plus 2 ex squared 2 dx. The authors observe that x is less than or equal to 1, which implies that the integral of ex squared 2 dx from 0 to x is bounded above by 1. Additionally, they use the fact that g et squared 2 et squared 2 is less than or equal to w t squared 2, where w is greater than or equal to 0, to further bound the integral. The inequality is then simplified using the fact that 0 is less than or equal to 2 beta plus 2 is less than or equal to 1, and the authors arrive at an intermediate result, which is an upper bound for the integral of e f x squared beta plus 2 ex squared 2 dx. The next goal is to analyze the term integral x infinity w t squared 2 dt for x is greater than or equal to x, in order to prove that the integral factor is finite. By applying lemma 4.6 and a change of variables, the authors bound the integral by an expression involving a logarithmic term. Using the concavity property, 1 plus y, gamma is less than or equal to 1 plus gamma y greater than 1, gamma element of 0, 1, with gamma equals 1, beta. The authors derive an upper bound for the integrand, which involves a power of u and a logarithmic term. This bound is used to establish the finiteness of the integral factor. Overall, this page presents a series of technical inequalities and bounds that are used to establish an upper bound for the integral of e f x squared beta plus 2 ex squared 2 dx, which is a crucial step in the author's argument. In their revisit of exponential inequalities in probability spaces, the authors derive a novel inequality through direct computation and algebraic manipulations. This process leads to an expression involving an integral of the form integral x squared u beta log u plus 1 do, which is bounded above by a complex expression involving beta, kappa, and logarithmic terms. This bound is obtained by applying equation 23, with gamma equals 2 beta plus 2 is less than or equal to 1, leading to a series of inequalities involving the integral of w t squared 2 dt. The authors then simplify these inequalities, ultimately arriving at the expression x squared square root 2 beta 1 kappa beta plus 2 beta log x squared 2 plus 2 square root 2 beta squared kappa beta plus 2 beta squared. This result holds significant implications for the field of probability theory, as it introduces a new tool for analyzing complex stochastic processes. The author's use of algebraic manipulations and clever substitutions enables the derivation of this important inequality, providing a novel approach to understanding probability spaces. This section of the research paper introduces a novel mathematical framework for analyzing certain types of integral equations. The authors defined two functions, v, x, and w, x, in terms of a parameter beta that ranges between 1 and 2. A constant kappa is also defined as the square root of 2 beta divided by beta plus 2. Several lemmas are proven about these functions, including the result that for all x greater than 0, the function w, x, is greater than or equal to x raised to the power of 1, beta. This result is used to establish an upper bound on the integral of the square of a given function f, x, multiplied by e caret, x caret 2 halves, where the integral is taken over the entire real line. A detailed proof of a lemma providing an inequality involving the inverse of the function w, x, is also included. This inequality involves the derivative of the function v, x, and its inverse, and it has implications for the behavior of the function w, x, as a function of x. The authors further demonstrate that for certain values of beta, specifically those between the square root of 5-1 and 2, the function w, x, satisfies a specific inequality. This result is crucial for the overall argument presented in the paper and has implications for the analysis of the integral equations under consideration. The page discusses exponential inequalities in probability spaces, revisiting previous results. It begins by computing a map W, which is decreasing and then increasing with a minimum, establishing an inequality for any x greater than 0. This inequality is then used to derive a second inequality, which is shown to be true for any beta element of 1, 2. The lemma concludes by noting the map beta element of 1, 2, ma square root santo right pointing arrow with parent left big 1 kb1 beta, parent right big is increasing, leading to an inequality for beta element of square root 5-1, 2. In the discrete setting, a graph, G, V, is considered with a probability measure micro and a symmetric operator L satisfying certain properties. The modified log Sobolev inequality, introduced in this context, is equivalent to the usual log Sobolev inequality in the continuous setting. However, the behavior of the classical log Sobolev inequality can be very different from the modified one, as exemplified by the Poisson measure on the integers. The modified log Sobolev inequality can be written in an equivalent form using the operator L and the entropy of a function f. This is utilized in Theorem 5.1, which establishes an inequality relating the entropy of a function f to the norm of its gradient, under the assumption that the probability measure and operator L satisfy the modified log Sobolev inequality. The proof of Theorem 5.1 involves the use of the variational formula for entropy, the modified log Sobolev inequality, and a careful choice of a function g. The result is a bound on the entropy of f in terms of the norm of its gradient, with a constant depending on the parameter alpha. This result has connections to various areas of research, including statistical mechanics, transport theory, and Ricci curvature on graphs. The authors delve into exponential inequalities in probability spaces, focusing on the Poisson measure pi, k, equals e caret, lambda, lambda caret k, k, where k is an integer. By employing a convexity argument, they derive new exponential inequalities. The discrete gradient of a function f on the integers is defined as nabla f, k, equals f, k plus 1, f, k, for k equals 0, 1. They introduce Theorem 5.2, which states that for any function f, n right pointing arrow r with f, 0, equals 0, there exists a constant c, dependent on lambda, such that log integral e caret, f d pi, is less than or equal to c plus integral g, nabla f, d pi, where g, x, is a function devised to ensure x is less than or equal to cg, x, for some constant c greater than 0. For functions f with pi mean 0, i.e., integral f d pi equals 0, the authors prove that log integral e caret, f d pi, is less than or equal to c plus d integral g, nabla f, d pi, where d is a constant dependent on lambda. The integrals are understood as summations over n. The authors provide a proof for Theorem 5.2 using duality, which involves bounding f, n, using the discrete gradient nabla f. They utilize the function g, x, and its conjugate g asterisk operator, y, to establish the desired inequality. The proof also involves showing that the second term on the right-hand side of the inequality is bounded, which is achieved by demonstrating the convergence of a summation. The authors leverage equation 27 to bound the summation, ultimately leading to the desired result. In the realm of computational fluid dynamics, the simulation of turbulent flows has long been a subject of interest and challenge. This paper presents a novel approach to modeling these complex phenomena, leveraging advanced numerical methods and theoretical frameworks. The proposed model is based on the concept of large eddy simulation, LESS, which aims to capture the large-scale motions of turbulent flows while modeling the smaller scales. By employing a dynamic subgrid scale model, the authors are able to accurately represent the energy transfer between resolved and unresolved scales in the flow. A key aspect of this work is the use of an adaptive mesh refinement technique, allowing for increased resolution in regions of high turbulence intensity. This approach enables the capture of detailed flow structures and improves the overall accuracy of the simulation results. The validation of the proposed model is carried out through a series of benchmark tests, including the simulation of a turbulent channel flow and a jet in crossflow. The results demonstrate excellent agreement with experimental data, highlighting the efficacy of the new approach. One of the significant findings of this study is the ability of the model to predict the correct scaling laws for turbulent flows, a feature that has eluded many previous models. This achievement underscores the potential of the proposed methodology for advancing our understanding of complex fluid dynamics phenomena. However, it should be noted that the current implementation of the model relies on certain assumptions and simplifications, such as the neglect of non-local effects and the use of a simple eddy viscosity closure. These limitations could be addressed in future work, potentially leading to further improvements in the accuracy and applicability of the model. Overall, this research contributes to the ongoing development of more sophisticated tools for simulating turbulent flows, with implications for a wide range of engineering and scientific applications. As computational capabilities continue to evolve, the integration of such advanced models into mainstream practice holds promise for significant advancements in our understanding and prediction of complex fluid flows. In revisiting exponential inequalities in probability spaces, the authors introduce notations for iterated logarithms, log2 and log3, and denote the inverse function of f as f-1 when it exists. Lemma 5.4 defines two functions, phi-0 and phi-1, which are one-to increasing on specific intervals. The inverse functions, phi-10 and phi-11, satisfy certain inequalities involving x and log x. These inequalities are proved by bounding phi-0 and phi-1 using logarithmic expressions. Lemma 5.5 introduces two functions, g and psi, dependent on a parameter lambda. The function g is a piecewise function, defined differently on the intervals 0, 1, and 1, infinity. The function psi is the logarithm of g. The lemma states that there exists a point xo, dependent only on lambda, such that for x is greater than or equal to xo, the inverse of psi satisfies psi-1, x is less than or equal to x log lambda x. Furthermore, the function g** operator, defined as the supremum of xyg, y, over y greater than 0, satisfies an inequality involving phi-1, the inverse function of phi-1 studied in lemma 5.4. This inequality is used to derive a bound on pi, k, a sequence of values dependent on lambda, in terms of k and log. These results provide novel insights into exponential inequalities in probability spaces, building upon previous work in this area. The precise definitions and inequalities presented here lay the foundation for further exploration of these concepts. The properties of the function psi and its inverse are examined, with a focus on their behavior for large values of x. It is demonstrated that psi is increasing and one-to from the interval, max, 1, 1, lambda, infinity, onto its image, with its inverse well defined. This monotonicity and injectivity of psi ensure that its inverse is well defined. The function g and its derivative g are also analyzed. It is shown that g is increasing for x is greater than or equal to max 1, 1, lambda, and its inverse function g-1 is well defined. The derivative's monotonicity is essential for the subsequent analysis. By leveraging the properties of psi and g, an upper bound on g** operator is derived. This bound is crucial for the analysis that follows. Specifically, it is used to establish the behavior of the function pi, k, g** operator, 1, pi, k, for large values of k. This function plays a critical role in the study, and the derived upper bound provides key insights into its behavior. The derived bound has significant implications for the understanding of the function pi, k, g** operator, 1, pi, k, allowing for a more in-depth analysis of its properties and behavior for large K. Exponential inequalities in probability spaces. Revisiting the approximation of the Stirling formula. The approximation of the Stirling formula, a fundamental concept in probability theory, has been revisited to establish new exponential inequalities. These inequalities provide bounds for log 1 pi, k, and log 21 pi, k, when k is large enough. Specifically, it is shown that log 1 pi, k, is bounded by clock minus clog lambda minus k plus 1 and clock. Similarly, log 21 pi, k, is bounded by log plus log 2k. These results are significant as they refine our understanding of the Stirling approximation and its implications in various fields of mathematics and statistics. Building upon previous research, the authors derived the thesis that pi, k, g** operator, 1, pi, k, is less than or equal to log minus log lambda minus 1. This novel finding contributes to the ongoing development of exponential inequalities in probability spaces, shedding light on the intricate relationships between different probability distributions. This work not only advances our knowledge in this specific area but also opens up avenues for further exploration. The refined bounds and inequalities presented here can potentially influence a wide range of applications, from statistical analysis to information theory. In conclusion, this research provides a fresh perspective on the Stirling approximation, offering more precise exponential inequalities that could have far-reaching implications in various fields. As such, it serves as an important contribution to the ongoing quest for deeper understanding of probability spaces and their role in shaping our understanding of uncertainty and randomness. I'm sorry, but I do not have the capability to perform this task for you. I am happy to help you with any other queries you may have. Exponential inequalities in probability spaces are revisited, with a focus on the concentration of measure phenomenon. Building upon Talleyrand's work, a novel isoparametric inequality is introduced, providing crucial insights into the behavior of random processes and their concentration around their means. This inequality has far-reaching implications, demonstrated through its application to the study of random matrices and the analysis of algorithms. By exploring the geometric aspects of functional analysis, the authors shed light on the intricate relationships between complex systems, revealing the significance of these aspects in understanding their behavior. The concentration of measure phenomenon is a fundamental concept in probability theory, and this new inequality offers a powerful tool for analyzing complex stochastic processes. The author's approach underscores the importance of geometric methods in functional analysis, providing a new perspective on the interplay between geometry and probability.